A machine learning ML engineer plays a vital role in designing, implementing, and optimizing machine learning models. Here are the top 10 tasks they typically perform. 1. Data collection and pre-processing, gathering and preparing large data sets for training machine learning models, handling missing data, outliers, and performing data normalization and transformation to ensure model accuracy. 2. Model development, designing, building, and training machine learning models using algorithms like regression, decision trees, clustering, deep learning, etc. Selecting the right model architecture based on the problem, e.g. classification, regression, clustering. 3. Feature engineering, identifying and selecting the most relevant features from raw data to improve the performance of ML models, creating new features from existing data to enhance model predictability. 4. Model optimization and tuning, fine-tuning model hyperparameters, e.g. learning rates, regularization parameters for better performance. Applying techniques such as cross-validation and grid search to improve model accuracy and efficiency. 5. Model evaluation and validation, assessing the model's performance using metrics like accuracy, precision, recall, F1 score, and raw CEC. Performing A/B testing to evaluate models in real-world settings. 6. Deployment of models, integrating models into production environments, ensuring they are scalable, efficient, and easy to maintain. Using tools like TensorFlow Serving, Docker, or cloud services, e.g. AWS, GCP, Azure, to deploy models. 7. Monitoring and maintenance, continuously monitoring the model's performance after deployment to detect issues like drift or changes in data patterns, updating models as new data becomes available to maintain accuracy and relevance. 8. Collaboration with data scientists and engineers, working with data scientists to understand the problem, choose algorithms, and prepare the data pipeline. Collaborating with software engineers to deploy models and data structure. Implementing both classical algorithms, like random forest, SVM, and advanced techniques, like neural networks, reinforcement learning. 10. Research and staying updated, keeping up with the latest developments in machine learning, deep learning, and AI by reading research papers, attending conferences, or taking courses. Experimenting with cutting-edge techniques, e.g. transformers, GPT models, GANs, to enhance ML applications. By executing these tasks, ML engineers ensure that their models not only perform well, but are also scalable, maintainable, and aligned with business goals. Machine learning models are generally categorized based on the type of task they perform and how they learn from data. Below are the main types of machine learning models and their purposes. 1. Supervised learning models. Purpose: learn a mapping from input features, X, to an output label, Y, using labeled data. Examples: linear regression, used for predicting continuous values, e.g. predicting house prices based on features like size, location. Logistic regression, used for binary classification, e.g. predicting whether an email is spam or not. Decision trees can be used. Support vector machines, SVM, used for classification tasks by finding the hyperplane that best separates different classes. K-nearest neighbors, KNN, a classification model that assigns labels based on the majority label among nearest data points. 2. Unsupervised learning models. Purpose: find patterns or structure in data without labeled outputs. Examples: K-means clustering, used to group similar data points into clusters, e.g. customers, PCA, used for dimensionality reduction and finding patterns in high-dimensional data, e.g. reducing features in image data. Autoencoders, used for unsupervised tasks like anomaly detection or data compression. 3. Semi-supervised learning models. Purpose: use both labeled and unlabeled data for training, typically a small amount of labeled data and a large amount of unlabeled data. Examples: self-training, starts with a small labeled data set, uses the model to predict labels for the unlabeled data, and then retrains. Graph-based methods, decisions by interacting with an environment to maximize cumulative rewards. Examples: Q-learning, learns optimal actions for each state by maximizing the expected reward, e.g. used in game AI. Deep Q networks, combines Q-learning with deep learning to handle complex environments, e.g. training autonomous vehicles or playing video games. Policy gradient methods directly optimize the policy that maps states to actions, e.g. in robotics or complex strategy games. How to 5. Ensemble models. Purpose. Combine multiple algorithms to improve performance and accuracy. Examples. Random forest, an ensemble of decision trees for classification or regression, e.g. used in fraud detection or medical diagnosis. Gradient boosting, e.g. XGBoost, Light GBM, builds models sequentially to correct errors from previous models, e.g. used in ranking tasks, predictive analytics. Bagging, e.g. bootstrap aggregation, reduces variance and overfitting by training multiple models on random subsets of the data, e.g. 6. Deep learning models. Purpose. Use neural networks with multiple layers to learn representations from raw data, often for complex tasks. Examples. Convolutional neural networks, CNNs, used for image recognition, object detection, and video analysis, e.g. facial recognition, autonomous driving. Recurrent neural networks, RNNs, used for sequential data like time series or language processing, e.g. language translation, speech recognition. Long short-term memory, LSTM, a type of RNN used for tasks that require long-term memory, e.g. stock price prediction, text generation. Transformers, used in natural language processing, NLP tasks, such as text generation, e.g. GPT, BERT for chatbots, and language models. Number 7. Generative models. Purpose. Generate new data samples that resemble the original dataset. Examples. Generative adversarial networks, used for generating realistic images, videos, and data, e.g. creating synthetic faces, enhancing images. Variational autoencoders, VAEs, used to generate new data points by learning the distribution of the training data, e.g. used for anomaly detection or creative applications. Each type of model is tailored to solve specific problems, from making predictions, supervised learning, to discovering hidden patterns, unsupervised learning, or making decisions, reinforcement learning. The choice of model depends on the task, data, and the desired outcome.